Unit 2B, Lesson 2. This lesson aligns with 5.3 in your textbooks. Two standards we're going to talk about. First one, apply concepts of density based on area and volume in modeling situations. The second one, which we're going to focus on mainly, is apply geometric methods to solve design problems, designing an object or structure to satisfy physical constraints or minimize cost. We refer to these design problems as optimization problems. Optimization problems are problems where we find the best solution out of all possible solutions. For example, maximizing the volume of a container with a given amount of material, or minimizing the cost of a product for a company. Most optimization problems are solved using calculus. So for those of you that decide to take calculus, we do a lot with optimization. For geometry, we could still do optimization problems. They're just going to be more basic and simple types of problems. We are going to go through one optimization problem. Suppose you want to build a fence around your garden to keep rabbits out. You have 60 feet of fencing and want to design your garden so that you have the maximum amount of area for your vegetables. So you want to determine the dimensions that will maximize your garden's area. The shape we're going to be working with is a rectangle. We have our length and our width. Two formulas we're going to have to use in this process. Area is equal to length times width. We need this because that's what we're trying to maximize. We also need the perimeter is equal to 2 times the length plus 2 times the width. We need this formula because that's the information we're provided with. We have 60 total feet of fencing, which represents the perimeter we're going to build. So the equation we need to start with is the perimeter equation because that's the information we know. So I'm going to substitute 60 in for the perimeter. Now we have two variables. We need to get one variable isolated by itself so that we can substitute that back into the other equation. So I'm just going to isolate L by itself. So I can subtract 2W to both sides. So 60 minus 2W is equal to 2L. Then to get L by itself, divide by 2, divide by 2. So L is equal to 60 divided by 2 is 30. 2 divided by 2 is 30 minus W. Now I'm going to use this expression on the left that I know is equal to L and substitute that in for L in our other equation for the area. So now we have the area is equal to, instead of L, we have 30 minus W times W. Using the distributive property, area is equal to 30W minus W squared. Now A and W, those aren't variables we use too often, but you should recognize what type of function we have right now. All this is a quadratic function, which we talked about in Algebra 1. And our A value, what's in front of our squared term, is negative. So if you recall from Algebra 1, if our A value is negative, our graph is going to open down. It's going to be a frown face. So if we're trying to find the maximum for the area, we have to find the peak of our graph, which is the vertex. Okay? So we got to go back, use all those ideas we learned in Algebra 1. We need to find the vertex for this graph. I'm sure all of you remember the expression we used to find the vertex. Negative B over 2 times A. Our B value is going to be 30. That's in front of our W to the first power. So this is going to be equal to negative 30 over 2 times our A value is negative 1. So 2 times negative 1. So we have negative 30 divided by negative 2, which is going to be 15. And that is going to be what our value for W is. Okay, so that will be the width. So maximizing our area, we found our width is going to be 15. Now to find our length, all we have to do is plug 15 in for W in this expression we already simplified. So 30 minus 15 is going to be 15. So L is equal to 15 as well. So the rectangular garden we can make that's going to maximize the area is actually going to be a square. So all side lengths being 15 feet will maximize the area of the garden. 15 times 15, you would have 225 square feet for your garden.